So we are going to start here. It is lecture number 35, and here we will talk about law of large numbers followed by central limit theorem and application of central limit theorem. So these are very important kind of approach that how you can calculate probability and how you can see the authenticity of that any estimator that you are getting from any sample. So coming to outline of, first I would like to discuss about law of large number. Afterward, I will talk about central limit. So coming to law of large number, a small brief I had already discussed in previous, but here I will talk from convergence point of view. Various actually I could not cover in last class various example of stochastic convergence. I had already told that in math 1 you had already gone through deterministic convergence. That means you are having a sequence of real number and you try to see that where that sequence is going to converge. But when you talk about sequence of random variables, then that deterministic convergence is not sufficient to describe the convergence of a sequence of a random variable. So you have to talk about the stochastic convergence. So various concept is coming that actually there are two approaches to describe that stochastic convergence. One we call it probability convergence in probability. Another we are calling it convergence in distribution. And apart from that, various other results, but these are two major stochastic convergence what we are discussing. So one example I had already taken that when what we call it in stochastic convergence, that when we are taking a sequence of very specified kind of random variable, that IID, that independent and identically distributed, and all these member of the sequence is having the common CDF f of x. So it is just one example I am taking it here because I have taken that all these member of the sequence is having common CDF. Then here we can claim that this sequence where it will convert to one random variable x with the same distribution. How we can see the convergency? It is very simple that we know that every member of the sequence of this random variable IID random variable is having the same distribution. So easily we can, if you are willing to find limit of this distribution function, it is a distribution function of xn. So if you are willing to find, we know that it is what it is same for every xn, and hence we can say that limiting value of this one would be just fx. So it is very simple example of a stochastic convergence. Further, if you take, we are taking another sequence of random variables. This one is example number 2. So here what I do, here I am taking a sequence of random variable with this is the distribution function, or this is even we can call it, it is a probability, it is distribution, simply we call it distribution. It is defined for positive x. Then afterward, what is happening that it is not density or probability mass function, it is distribution function, capital F would be there. So if you are trying to find limiting value of this distribution function and with respect to n tends to infinity, what we see here, it is approaching to 1 minus e to the power minus x, and that one is actually what it is distribution function of the random variable x. Here what is x? X is the limit of xn, and if we are calling it x is the limit of x and this sequence of random variable, the limit in what kind of stochastic convergence? It is in distribution. So we will put it here, here D. So all these are example of the stochastic convergence. Further, if you take a limit sequence of random variable like this one in such a way, this each member of the sequence is coming from a binomial distribution with parameter n and probability of success. This lambda by n, we are calling it probability of success. Why? I will try to relate it with what we call it exponential random variable. That's why I am taking in that. So here we can say that probability of success is equal to lambda by n. Okay. A Poisson distribution, we will try to relate it. So okay, so what is happening that here? So all these xi, this xn are what binomial random variable and having probability of success lambda by n. That means function of n. So we will try to take limit of the what we call it distribution function. It will define in terms of probability. So we are trying to take limit of, so here probability distribution is given by this one, and this is that probability distribution for binomial distribution, for any binomial distribution. So we are trying to take limit n times to infinity. If you are taking limit n times to infinity, where it will converge to this distribution, this probability mass function, and it is what? It is probability mass function of Poisson distribution. We can easily see that. So one approach we had already discussed that. So what in that case I had told that when n is very large and the probability of success happens to be very small, in that case a binomial distribution can be approximated well by Poisson distribution. The same criteria is coming through stochastic convergence as well. So we can say that the sequence of binomial distribution is converging to the Poisson distribution with convergence is it is with respect to distribution. It is coming with respect to distribution. So another example I would like to take it like this way. This one is example third or fourth it would be. So if we are taking a sequence of exponential random variable, and here what is that? Each member of the sequence is having parameter lambda equal to m. Okay, like this. So definitely it is a function of m. So we will claim that this sequence is going to converge to constant random variable x equal to 0. So it is very simple to, so we will prove this one through convergence in probability. So how we define in convergence probability? That means we know that we know the limiting value of x, and where it will converge to 0. So that's why we are defining this. That means in the neighborhood, a small epsilon neighborhood of 0, we are defining x and such x and all most all after leaving few terms of x and most of terms falls in the neighborhood of 0. That directly coming from sequential deterministic sequential criteria. But here we are talking about stochastic conversion. So we will add here probability, convergence in probability. So we are adding here what is the probability that leaving few terms, few first term, afterward rest of terms falls in the small epsilon neighborhood of 0. What is the probability of that? The probability we calculate it with respect to n tends to infinity, and when we are going to calculate it, so this probability is equal to this probability. Both are simple. That means it is just talking about what is the probability that xn is away from 0, epsilon away from 0. So it is saying that xn is within epsilon neighborhood of 0, and this just both are equivalent to each other. Uh, so the equivalent in sense that when it will approach to 1, then this will approach to 0. That is the equivalency what we say. We want both are not same. So this one is talking about what it is talking about probability up to epsilon. This one is talking about probability that right tail and left tail probability. So it is very much simple in normal distribution. You had already seen that. If you see the normal distribution plot of the density of normal distribution, what you observe that? You observe that either you calculate this tail probability, this right and left tail probability, or you calculate this probability. Both are equivalent to say. So in order to say that most of the area contained in here, what does it mean? It simply say, just prove that the area contained in left and right tail is 0, almost 0. That means equivalent. That means most area are covered. Are coming here in this region. So that is the equivalency I would like to say that. So that's why because this region is easy to establish. That's why we are going for that. We know that here xn is exponentially distributed with mean lambda equal to m. That means most of the value of xn is distributed around n. That means n is a positive natural number. Natural number. So what will happen? This modulus of xn it would be just xn. That's where we are coming. And what is this? This one is very easy to calculate. This probability that xn is greater than equal to epsilon. What does it talk about? It is talking about right tail probability, and in exponential. In right tail probability, we had already seen that this right tail probability we can easily express. Okay, we can this probability we can easily express how e to the power minus lambda times s. Lambda is equal to what? N. So lambda, in place of lambda we will put it n times s. So same thing is written here, and we are taking limit n times infinity. So what is the limiting value of this one? It will converge 0. So easily we have already established that sequence of exponential random variable with this kind of parameter is converged 0, and but convergence is in probability. So we are here we are establishing convergence in probability. Further, we had already discussed about law of convergence, law of large number in two different approaches. Law of large number simply it is saying that that sample mean, this sample mean x and bar, it is converging to true mean of the distribution mu as n tends to infinity. But convergence, remember that this convergence happens in stochastic manner. So convergence actually this convergence generally always happens in convergence probability. So that convergence probability approach into different way. One is strongest, that we just talked about deterministic convergence of this sample mean, this action bar, we can relate it to 1 by n summation of xi, I is very equal from 1 to 1. So deterministic limit of this one equal to mu, and what is the probability of that? What is the probability that deterministic limit of the sample mean is equal to mu? That probability is equal to 1. So this convergence we are calling it stochastic convergence, and if you try to establish this one, it would be definitely relatively hard. Then weaker version is coming like this way. It is talking about this is simply convergence in probability. That means what is the probability when n tends to infinity? The sample mean is very near to epsilon. That means epsilon near away, within epsilon distance of mu. What is the probability that sample mean? This sample mean we can put it xn. Sample mean is within epsilon neighborhood of mu. So that probability is equal to when n is very large. So that is that. And this concept is relatively easier to establish. So this is what I am calling it law of large number. Directly I will go to cover about central limit theorem. Okay, this one is main part of this lecture. So what does it say? Here it is also talking about convergence, but convergence in distribution. Central law of large number was discussing about convergence in probability. Central limit is discussing about convergence in distribution. So consider a sequence that finite sequence, or simply you can say that a sample of size n. That means you are taking a sample with n observation, and each observation happens to be IID, independent and identically distributed. That means we are having a distribution x, having a random variable x, whose distribution we don't know. That is the criteria. We don't know what is the distribution of x. So what we do, we have taken n observation of x, n copies of x. We can say that in that process to form a sample of size n, all possible sample of size n. So we are getting a sample of size n. So and what is happening, that we know that mean of this one is mu and variance is sigma square. That we know that, but we don't know the distribution. So in order to know the distribution, what we do, we will define. Don't worry to find actual distribution of x. What we will do, in place of finding the distribution of x, we will try to find the distribution of sample mean. So we are defining a sample mean from these observations. So this is the sample mean, x and bar is the sample mean, and here we will talk about when we standardize the sample mean with mu and sigma. This we are calling it standardized sample mean, and in that process, if you are defining, this is what it is, the distribution function probability up to this point. That means talking about distribution function of standardized mean. When n is approaching to infinity, this distribution will approach to this distribution, that distribution of a standard normal random variable, that we can denote by phi of z. So if you talk about what is convergence, here convergence, it happens in distribution. That's why if someone is asking what is the difference between law of large number and central limit theorem, the simple difference is that law of large number is talking about convergence in probability, and central limit theorem is talking about convergence in distribution. Both are dealing with sample mean. Definitely both are dealing with sample mean, but approach, convergence approach is different. Okay, so one example here I am taking. Suppose x1, x2, xn, one sample of size n we are taking from Bernoulli distribution with probability of success p, and hence we can say that the true mean of the x would be what? P. But we don't know the distribution right now. Just say that we don't know the distribution, but we know the distribution mean of x. That one is p. Variance of x. That one is p into 1 minus p. That is we know from the nature of Bernoulli variance, and mean would be like this. Okay. So we try to we don't try to find the distribution of x. What we will do, in place of finding the distribution of x, we will find the distribution of sample mean. So we are finding the distribution of sample mean through this convergence approach, central limit theorem. So here we are deviating the sample mean by mu and dividing by the what standard deviation of sample mean. This is the mean of the sample mean, and this is the sigma by square root of n is the what we call it standard deviation of the sample mean. So definitely it will converge to the distribution of standard normal random variable, and this convergence is what it is in. So here I am taking one example, then application of that central limit theorem would be more clear. So suppose question is coming like this way: there are 100 men on a plane, and let xi be the weight of the ith man on the plane, and suppose that xi's are IID. That means all xi's, that is all weight of each person is independent and identically distributed. That means coming from the same source. Distribution is coming from the same. Each xi is having the same distribution. Only information we are having that what is the mean weight. Mean weight is 170, and what is the standard deviation? Standard deviation is 30. You can take unit. Unit is given in form, but unit is immaterial to proceed with here. So we have to find the probability that total weight of the main, okay, on the plane exceeds 18,000 pounds. So we have to find the probability that total. So we can denote it by W. W is what? Sum of all xi. You can say that. So we have to find the probability that this W is greater than equal to. What is the probability that W is greater than equal to 18,000 pounds? We can leave the unit. So this probability we have to find it. Here remember that we don't have given distribution, just mean and standard deviation is given. Apart from that, we don't have much information. And also how many how many terms, what is the sample size? Sample size is 100. That one is also given. Okay, n is also given. So using all this concept and central limit theorem, we can easily calculate this distribution of W. Okay. Simply our desired thing is that we need to calculate this probability. So we are defining W as a sum of all these weights, W1 plus W2 up to W100. Then easily we can calculate expectation of W. What would be that? Expectation of W, we can calculate it. It would be we know that each xi and hence xi I have changed the notation. X1 I have denoted by W1, X2 I have denoted by W2, and Xn has been replaced by Wn. Okay, so we know that each xi happens to be independent and identically distributed. So the mean of W, it would be n times mean of xi. That means n times 170, and in total we are n is what, 100. So in total we are getting mean of the W is what, 17,000. Likewise, also we can calculate variance due to independent nature. Variance of W would be 100 times a square of 30, and that means 90,000. So and hence we can say that what is the variance, standard deviation of W? It is 300. We got all the required things in order to find this distribution of W. So what will happen? So that means in order to calculate desired probability, that probability we are going to calculate that what is the probability that W is greater or equal to 18,000. So simply we have to perform standardization. So we are here performing standardization by using the mean of W and dividing by the corresponding standard deviation. So we do perform standardization, and hence what will happen? This will approach to Z when n is approaching to infinity. When n is approaching to infinity, this will approach to. So here we can talk about n is approaching to infinity. That means we are talking about approximation. So here this one is approximately. This probability can be approximated by. So what will happen? So it just this probability, what it would be? It would be equal to probability that Z is. This has been what? It has been converted to W in D. So we will replace W minus 17,000 by 300 as Z, and in right hand side if you calculate, it will come as 10 by 3. Now this probability, it is talking about this approximated probability, it is talking about a right hand probability. So we always express this one as a what? Probability that Z is taking value less than equal to 10 by 3. You can convert, and what what is name of this one? This one simply we are calling phi of 10 by 30, and we can get value of this one from the normal table. And if you calculate, then approximated value of the desired probability, it is coming around what? This point 4.3 into 10 to the power 4. This is very less amount of probability this one is coming. So we can calculate the probability of any distribution of sum of distribution without knowing the distribution. Without knowing this, that is, so it is an application of central limit theorem. I will take another example. So here, suppose we are having a sample of size n, that means 25 observations we are having, and each one is having probability mass function like this way. This is the probability mass function for each one. Okay, and here we are defining some of these ID random variable. Okay, so our idea is that we have to calculate what is the probability of y. Here we don't know the distribution of y. Okay, we have to calculate the probability of y. How we can calculate probability of y, that y falls between 4 to 6. So again we will apply central limit theorem here. So it is easy to calculate mean and variance of xi. So first moment would be mean, and that one is 0.2. Second moment would be what? This one would equal to 1. Easily we can calculate due to properties of xi is given by this one. It is already given. Okay, distribution is already given. The probability mass function is given, and from there we can derive variance of xi. That would be 24 by 25. So we know the mean and variance of xi. So using that concept and ID nature of xi, we can calculate the mean of the sum of these ID, that would be 5, and variance would be 24. So variance of y would be 24. So here regarding y, we don't know the distribution of y, but we know the mean and variance. So here we will apply central limit theorem again in order to calculate the desired probability. So what we do? So we are calculating this probability. This probability would be, if you talk about in continuum fashion, then we talk about 0.5 liberty, that shifting. Okay, so it is y is taking value between 4 to 6. So we can take in continuum fashion, we can define it like this way. 0.5 we can include in order to make it continuous pattern. Okay, after that what we do? We do rationalization. So rationalization we are doing like this way. That means we subtract, we deviate the y by corresponding mean of y and divide it by the associated standard deviation of y. So we did that. In the process of that, these limit, right hand limit and left hand limit, both will be modified. And if you try to see that in convergence probability, where it will go to converge Z in distribution. Okay, so that means this probability, the desired probability, can be approximated by the probability of a standard normal random variable that Z is taking value up to. You can see that this quantity would be negative of it is negative of 0.3062, and this one would be positive of 0.3062. That's why I have taken it in modulus form, and easily we can calculate this from the normal table. This probability would be 0.2405. Okay, so all these calculation we are doing without knowing the distribution of actual thing for which what we want to calculate probability. So here all these are application of central limit theorem. So I will talk about a few more applications. Here suppose you have invited 64 guests to a party. Okay, and you need to make sandwiches for your guests. Okay, so you believe that these are the assumptions. A guest might need either 0 or 1 or 2 sandwich with probability 0 probability sandwich with probability 1 by 4, 1 sandwich with probability 1 by 2, and 2 sandwich with probability 1 by 4. That means each guest is having a probability distribution for sandwich. And that means if you talk about xi for ith guest, then xi will take 3 values: 0 with probability 1 by 4, 1 with probability 1 by 2, and 2 with probability 1 by 4. So that distribution is very much given. Okay, now question is different. Question is something like that. You assume that the total number of sandwiches each guest needs is independent from the other. There is no dependency. ID situation we are taking here. Okay, so here we have to calculate how many sandwiches should we make to so that 95% sure that there is no shortage. That means with 95% confidence we can say that there would be no shortage. So that confidence thing I will discuss later. That just you have to find the probability that how many sandwich you need, number of here, and you have to find what is the sample size. We don't know the sample size here. What would be the sample size, that what would be the desired n, so that we will be 95% confident that there would be no shortage. That 95 one n is given 64, but this one is that we are willing to find 95% confidence that there would be no shortage. So in order to calculate this, simply we are defining y as a function of it is just sum of all these 64 in IID random variable, and our goal is that we have to find y, that is what is the size of sandwich, so that it will we will 95% confidence. That means we are willing to find this y, this value of y. We don't know this y, that we have to find the probability that this random variable y is less than equal to y uh, within 95% confidence, or just 95 up to 9, or what we call it 90 95 greater than equal to 95%. Okay. So that we, so here y is unknown to us. We don't know y. We have to calculate. So how we can calculate? Again, we can calculate with the help of central limit theorem. So first, in order to calculate apply central limit theorem, we have to calculate mean and variance of each individual member of the IID. That's okay. So mean of xi would be equal to 1 due to the given distribution, because xi is taking value 3 value. It is taking 0 with probability 1 by 4. So directly you can say that it is what probability mass function of xi. You can say that. Okay, it is taking value 0. It is taking value 1 with probability 1 by 2, and 2 with probability 1 by, sorry, 1 by 4. So this distribution is given with probability, you can write it with probability. Okay, so we come to see that mean of xi is 1 and variance of xi is 1 by 2. Using this, we can calculate mean of y. So what is the mean of y? It is just xi is independent identically distributed. So mean of y, it would be 61 times mean of xi. That one is 1. So that means mean of y is equal to 64. Likewise, variance is equal to 32, and hence we can say that what is the Aston's division of y? It is 4 times square root of 2. So we are having information about mean and variance of y, but we don't know the distribution. So we will talk about convergence in distribution to Aston normal random variables. So again, we are defining like in the same situation, we are going to calculate probability that y less than equal to y, and we know the value of this one. It is what is greater than equal to 0.95, but we don't know y. So we need to asterize this one. So we are asterizing like in the same fashion by utilizing mean and variance of y, and in that process, this would be what? This would be converted into that that distribution function of the value of pi at z equal to this one. This you can see that it is z equal to 1. Z equal to y minus 64 divided by 4 square root of into square root of 2, and it is talking about convergence in distribution, and value of this one is given 0.95. This value is given. So we have to apply that inverse this pi approach. From there we can conclude that value of y would be 73.7. So this much of sandwich you have to order. You have to make it ready for your guest. Yes, so that there would be you would be 95% what we confident there would be no shortage. Okay. Other things we will discuss in next class. Thank you for your patience and attending this lecture. And if you are having any question, you can ask.